All right, let's dive right into this explainer. Today, we're building a rock-solid foundation for understanding classical physics by unpacking the exact definitions of work, energy, and power. Now, these are words we throw around in casual conversation all the time, but as we're about to see, the universe actually has some very strict, mathematically precise rules about how they operate. So think about what you're doing literally right now. You might be racking your brains, studying for a huge exam, or maybe you're just intensely staring at a screen trying to absorb this information. It feels exhausting, right? But mathematically speaking, are you actually doing any work? To figure that out, we've got a great roadmap today. We're going to cover physics versus everyday work, the math of work, kinetic energy in action, storing potential energy, and finally, conserving mechanical energy. Let's kick things off with Section 1, Physics versus Everyday Work. We really need to completely dismantle our everyday idea of what working actually means. You know, a farmer plowing a hard field, an artist painting a landscape, or you agonizing over a textbook. Sure, in everyday language, that's working. But physics? Well, physics, frankly, doesn't care how tired you feel. In the realm of physics, work has a strict, uncompromising definition. It absolutely requires a defined force acting over a physical displacement. There is, at best, a very loose correlation between your physiological feeling of exhaustion and actual mathematical work. Here's where it gets wild. You can exert a massive amount of physical effort, but your work mathematically vanishes into thin air if you hit any of these three conditions. First, if the displacement is zero. You can push against a solid brick wall until your muscles literally give out, but if that wall doesn't move, you've done zero work. Second, if the applied force is zero. Picture a block sliding across a perfectly frictionless table. It's moving, sure, but with no horizontal force acting on it, no work is being done. And third, if the force and displacement are mutually perpendicular. Think about the moon orbiting the Earth. Gravity pulls it inward, but the moon moves tangentially. Because of that exact 90-degree angle, Earth's gravity does absolutely zero work on the moon. To put that into perspective, imagine a massive weightlifter holding a 150-kilogram barbell steadily above their head for 30 agonizing seconds. They are sweating, their stamina is draining, but guess what? They are doing exactly 0 joules of work on that load. Since there's zero displacement while holding the weight steady, the equation dictates that zero work is happening. Crazy, right? Which brings us right to Section 2, the math of work. To understand why that weightlifter gets absolutely no mathematical credit, we have to look at the scalar product, also known as the dot product. Work is a scalar quantity, meaning it has a magnitude but no direction, and it's the dot product of the force and displacement vectors. It's defined as the magnitude of force times the magnitude of displacement times the cosine of the angle theta between them. That angle, theta, is everything. If you push something straight ahead, you get maximum work. But if you're pushing at a 90-degree angle, well, the cosine of 90 is 0, and the whole shebang multiplies out to 0. Now watch how beautifully this logic builds on itself. We start with a classic one-dimensional motion equation from kinematics. If we take that and just multiply both sides by half the mass, we elegantly arrive at the work-energy theorem. By substituting in Newton's second law, mass times acceleration equals force, we see that the final kinetic energy minus the initial kinetic energy perfectly equals the work done. Put simply, the change in an object's kinetic energy is exactly equal to the work done on it by the net force. Moving right along to Section 3, kinetic energy in action. So we've mathematically linked work to motion. Now let's talk about the energy of the now, kinetic energy. If an object of mass m has a velocity v, its kinetic energy is simply 1/2 mv squared. It's a scalar measure of the work an object can do simply by virtue of its motion. And humanity has intuitively understood this for a really long time. We use kinetic energy for everything from grinding corn in a fast-flowing river to sailing huge ships on the wind. Let's put some real numbers to this to see the sheer scale of it. Consider a tiny 50-gram bullet fired at a speedy 200 meters per second. That little projectile packs a massive 1,000 joules of initial kinetic energy before it even hits a target. And quick side note, the joule is our standard SI unit for work and energy, named after physicist James Prescott Joule. Now, if that bullet hits a block of soft plywood and emerges on the other side with only 10% of its initial kinetic energy, its speed drops drastically. Why? Because the work done by the wood physically stripped that bullet of its kinetic energy. But what if things aren't moving? That brings us to Section 4, storing potential energy. The very word potential suggests a possibility or a capacity for action. If kinetic energy is the energy of the now, think of potential energy as the later. It's basically a bank account of action just waiting to be spent, stored up simply by an object's position or configuration. Think of a tightly stretched bowstring right before the archer lets the arrow fly. The second those external constraints are removed, boom, that stored energy is released as kinetic energy. I absolutely love this terrifyingly perfect analogy from the source text. Discontinuities and dislocations in the Earth's crust create fault lines, right? Well, those fault lines act like massive, subterranean, compressed springs. The ground literally beneath our feet is holding onto an immense amount of stored potential energy, just waiting for the pressure to get too high. An earthquake is simply the violent, kinetic release of all that pent-up tension.
And speaking of springs, let's look at the actual math of a stretched or compressed spring. It is defined by Hooke's law. Force equals negative k times x. That k is the spring constant, which just measures how stiff the spring is. Now, when you pull a block attached to an ideal spring outwards, the work done by the spring itself is actually negative. Why? Because the spring desperately wants to snap back in the opposite direction. But the work done by your pulling force is positive, and all that effort gets securely locked inside the spring as stored potential energy.
All right, let's tie it all together in our final section, conserving mechanical energy. Here is the absolute magic of physics. As long as the forces involved are conservative, energy isn't created and it isn't destroyed. It just perfectly shapeshifts. The total mechanical energy, which is just the sum of kinetic energy K and potential energy V, remains completely constant. Individually, the kinetic and potential energies might wildly swing up and down as things move, but their combined total, it never, ever changes. This dropping ball perfectly visualizes that conservation law. Imagine holding a ball at the top of a cliff of height h. Before you let go, it's stationary, so kinetic energy is zero. All its energy is pure gravitational potential energy. But the moment you drop it, as it falls through midair, it speeds up while losing height. That potential energy is smoothly converting into kinetic energy. Right before it smashes into the ground, its height is zero, so potential energy is zero, and it's 100% kinetic. But all the way down, the total energy amount remained exactly the same. Now, a quick caveat. This pristine conservation only applies to conservative forces, like gravity. A force is mathematically conservative if the work it does depends solely on the initial and final positions, completely ignoring the path taken. If you release an object from rest at the top of a smooth, frictionless ramp, its speed at the bottom relies purely on the height, regardless of how steep the angle is. But this nice, neat rule doesn't apply to messy, non-conservative, path-dependent forces. Which brings us to a really fascinating final thought. Think about a cyclist slamming on the brakes and skidding to a stop. That frictional force directly opposes the motion, creating an angle of 180 degrees. The cosine of 180 is -1, meaning friction is doing negative work and sapping the cyclist's speed. But where does that energy actually go? Does the universe ever truly let energy just disappear? If mechanical energy isn't conserved when friction crashes the party, what form does that missing energy take? I'll leave you to ponder that profound question until our next explainer. Keep learning and stay curious.